Hello, welcome to Engineers Mindset. In today's class, I'm going to teach us how to derive the bending equation. Now, as we all know, whenever any material, or let's say a beam, is subjected to load, as can be seen on the board, whenever a beam is subjected to load, there is a high possibility of what? Deflection or bend. That bend gives rise to what is called an arc, okay, as can be seen. So this load is applied on this beam, and due to this load now, there is now a deflection about the neutral axis, okay. There's now a deflection about the neutral axis, simply causing the load to form an arc due to the bend. Now, because of this arc, we are simply going to have what is called an arc angle, and then we're also going to have what is called the radius of curvature due to what? The arc that is formed. Okay, so the arc angle is formed here. I'm able to trace out this point here. That's the center of the cycle or the arc. Okay, I will simply have an arc angle here. Simply call this angle theta. And of course, the line from the center to any point on a cycle or to any point on an arc is simply called the radius arm. And that radius in this case is called the radius of curvature. So we simply replace here with simply r. So the distance from the center to any point on the arc is simply called the radius of curvature. Now, if we assess this beam, we have said let us consider a thin strip of thickness dy. So we have the thickness here given as dy. Okay. Okay, we have the thickness simply as dy. Okay, a thin strip of the rectangular beam itself. We are considering a smaller portion of it, and then we are saying let the thickness of this smaller portion simply be what? Dy. Also, the neutral axis is simply what? X and N. That's the middle point. The neutral axis is that point where bending is maximum. That is to say, it is also the point where bending takes place. So, neutral point on the beam is simply, neutral axis is simply SN. Okay, as can be seen here, that's the middle portion of the beam. That is where bending becomes maximum. We are also saying that let the distance from the neutral axis to any of the points simply be what? Y. So we are simply saying from this point to this point is Y. Also from the neutral axis downwards as well can also be called Y. That's the distance, okay? Okay, that's the distance from neutral axis to any of these points on the rectangular beam. All right. Now this load causes a deflection, and then we form this arc. This is called the arc angle. Theta is equal to the arc angle. Okay, theta is simply the arc angle, and r is simply the radius of curvature. R is simply the radius of curvature. Okay, r is simply the radius of curvature. Now, if we say that from A to the middle point or the neutral axis is simply what? Y. That is the depth of the rectangular beam from point A to the middle point or the neutral axis. We simply call that Y. Then what now happens? If I trace this point now, if I trace this point down to the neutral axis, if I trace this point down to the neutral axis, notice that I said from the center to point A after the bend, now we have A prime, B prime, C prime, and D prime. Okay, so from the center to point A prime, we call that what? The radius of curvature. So if we are simply saying from A to the neutral axis is Y, now from the center to the neutral axis simply becomes what now? It becomes simply what? R plus Y. That becomes the distance from the center to the neutral axis. Okay, if from the center to A prime after the bend, we call it radius of curvature, which is r due to the bend, of course. Now from the center to the neutral axis, which is now x prime and m prime, that's the middle point of the beam where bending is maximum, is simply going to give us r, because from point A down to the neutral axis is simply what? Y. Okay, let me indicate that here. From this point to the neutral axis is simply Y. Okay, so that means from the center to the neutral axis simply becomes the sum of the radius of curvature and that depth Y. So that simply gives us Y plus R. Okay, so we have this now. So to prove this equation, first thing first, I've always said that whenever a beam is subjected to load, two things play out on the beam. First thing is that the beam is strained, and the next thing is that the beam is also what? Stressed. So we are going to obtain the strain and the stress due to this load that is being applied on this beam that causes the beam to bend. We have to obtain the strain. We also have to obtain the stress. Okay, let's do that now and see. Okay, so after the bend, the beam forms an arc. Okay, so it forms an arc now, and therefore the arc length gives us the initial length of what? The beam due to what? The bend from the center. And the arc length is simply given as arc length, okay, is simply equal to the radius times theta. This arc length is simply the same thing as the initial length due to the bending. That is from the center to point A, or A prime now. That gives us the initial length due to the bending. So we can now simply say initial length is equal to the arc length. Okay. Initial length is simply equal to r theta. So we have this. Now the final bend is the bend about neutral axis. That is where bending is maximum. So that length is about the neutral axis. And we said from the center to the neutral axis, the radius is simply radius of curvature plus what? Y. That gives a total distance from the center to the neutral axis. Therefore, we can obtain the final length. It's still going to be an arc. Final length is now, okay, simply that radius from the center to the neutral axis, and the radius is actually a sum of r plus y. So we simply put that down, r plus y multiply also by theta, because it's also an arc length. So we simply have r plus y multiplying by theta. All right, so if you have this now, it means we can obtain the change in length, because we have the final length, we have also the initial length. So we can actually obtain change in length. Okay, change in length is simply equal to the final length. Okay, let's simply use LF minus initial length Li. Okay, where LF stands for final length, Li stands for initial length. Therefore, change in length, this implies that change in length is now equal to the final length. We call it to be r plus y multiplying by theta. So we simply have r plus y multiplies by theta minus the initial length is simply r theta. So we simply have r theta. Okay, so if we now expand this bracket, we are going to find that change in length is now equal to r multiplied by theta, simply gives us r theta, okay, plus y multiplied by theta gives us y theta, okay, minus, then put down this r theta. So from here now, it is very visible that r theta can subtract r theta and is off. R theta minus r theta is gone. So it simply means that we have change in length to now be equal to simply y theta. So let's keep this equation here. R theta minus r theta becomes 0. So I'm left with simply what? Y theta. That becomes my change in length. But recall that strain is actually what? Change in length all over what? The initial length or original length. That's the symbol for strain, or that's the formula for strain. Change in length with respect to the original length or the initial length. Therefore, this simply now implies that I can now find strain to now be equal to change in length. We obtain that to be y theta. So it simply becomes y theta all over original length or initial length was obtained as what? R theta. So we simply have that to be r theta. So notice here that theta can cancel theta. So I'm simply left with what? Y all over r. Okay. All right. So strain is simply what? Y all over r. Let's call this equation 1. But recall that Stress itself is simply strain times Young's modulus. So I've always said that whenever a load is applied to a material or a beam, we must always have what is called the stress and the strain. The load must cause a strain on that object or the material, and at the same time, it must also cause a stress. So if we found the strain, it is wise for us now to obtain what stress is. We know from Young's modulus simply that we can make stress subject, and stress is simply strain times Young's modulus. Okay, therefore stress, which is sigma, is now equal to, okay, in place of strain, we simply put in the value now. We've obtained strain as simply y all over r, okay, times Young's modulus, which is this. So let's say we cross multiply this equation. Let r multiply by stress. Of course, this is simply stress all over 1, still the same thing. So I can easily cross multiply here. 1 multiplies the whole of this value, stress multiplies the whole of this value. So I'll simply have stress multiplies by r, and that's simply equal to y times Young's modulus multiplied by 1, which gives us y times Young's modulus. Now, if I decide to divide both sides by y arrow, let's say divide both sides, okay, both sides by y arrow, I'm simply going to have stress all over r divided by y r, and this is equal to ye all over y r. So from here, notice that radius will cancel radius out, and here y will also cancel y out. So I'm simply left with what? So I'm simply left with stress all over y here, all over y is now equal to E all over R. So I'll have E divided by R. Let's call this equation 2. Okay, let's call this equation 2. We'll keep that equation now apart, and let's now obtain the next thing. All right, so now after obtaining this relationship for the stress, the next thing we have to find now is the moment caused due to the load. So I've said that whenever a material is loaded, of course, we have strain. We've also proven that we have stress. We've shown that. The next thing that happens now is that there is going to be what is called moment of resistance. These moments are due to forces that emanate from what? The central or the neutral axis. So those forces resist or causes a moment that resists the what? Load that is being applied on the material. So it's called moment of resistance. We need to now obtain what is this moment of resistance. So what we'll do now is we'll now recall the beam again. We consider a beam which has a width. Let the width now be simply what? Small letter b. Let's simply use small letter b to replace the width of that beam. The thickness doesn't change. Thickness, recall from beginning, we said thickness remains what? Dy. Okay. So we are going to now what? Introduce this beam showing this small element of forces that's acting at the middle portion of the beam that causes an opposing moment against the load that is being applied to the beam. Let's do that now and see. Okay, so I have the same rectangular beam, doesn't still change, A, B, C, and D. And also, this remains the neutral axis where bending is maximum. So we call this SN. Neutral axis is always at the middle. That is where bending is maximum. Now, let's consider a thin portion of thickness dy. Let's consider a small portion here of thickness dy. Okay. So we simply consider a small portion. The thickness of this portion is simply dy. We said this from beginning. Now, let forces emanate from what? The neutral axis. These forces actually cause what is called resisting moment. So let's call that force dF, force is a combination of different smaller intensity of forces. So let's simply call it is a derivative, simply what? df. Now, let the height always remains what? Simply y, it doesn't change from A to the neutral axis. We call that distance y, so it doesn't change. We have this. And we said let the width be simply what? B. Okay, so the width from point A down to point B, the width of this rectangular bar is simply what? B. We called it B. Okay, this is now the width B. All right. Now we know that moment M is equal to force times what? Distance traveled. Okay, force times distance traveled. Okay, we know that moment is simply force times distance traveled. In this case now, the force is a small force, so we'll call it the F. It means the moment is also going to be a small moment. Therefore, we are simply going to obtain the M, which is smaller moment, is now equal to, due to what? The small intensity of force acting at the neutral axis. It's now going to be what? The F times distance traveled. Now, the distance is simply what? Distance from the neutral axis to any point on the beam. So we said from neutral axis to either point A, distance traveled is simply what? Y. Also, from neutral axis to point D, distance still remains Y. It doesn't change. So therefore, the M is simply what? The F times that distance is now what? Y. So we have this. Okay, now how do we then get what? The F, which is this force now. Let's call this equation 3. Let's call this equation 3. Recall again that stress, we said stress, which is rho, is simply what? Force all over area. This simply gives us the formula for stress. So which means if we make force subject, this simply means force is now equal to what? Simply what? Stress times area. Force simply gives us stress multiplying by area. That is force. Okay, so therefore, if the force here is a smaller intensity of force, it means that the F now is simply equal to what? Stress times the A. So which means if the force is smaller force, it means it will also act about a smaller what? Area. So the F is simply what? Stress times the A. Okay, so we can now substitute this equation into equation 3 in place of the F. Simply put stress times the A. Okay, let's do that now and see. So if we substitute this value for the F into equation 3, we are simply going to have the M is now equal to, in place of the F, we'll simply put in the value as stress times the A. So that simply gives us stress multiplies the A multiplies by Y. So we have this. Okay, let's call this equation 4. Let's call that equation 4. Now, recall from equation 2, we can make stress subject, because from here, we can simply send y over here and make stress subject. So from equation 2, okay, we can obtain that stress itself is simply equal to, all right, simply send y here, it becomes y times Young's modulus all over the radius of curvature. This becomes the value for stress. Simply, we substitute this value into what? Equation 4 in place of stress. If we do that, we are simply going to have that the small intensity of the moment, the M, is now equal to, in place of stress, this becomes y times Young's modulus all over r, okay, times the A, okay, times y. So we simply have this. Let's also call this equation 5. Now, let's obtain the value of the A. That's a small amount of area. Of course, we know that area is simply what? Width times thickness. That gives us the area. In this case now, the thickness we said should be what? Dy. It was stated from beginning. The thickness is dy. The width of this beam is given as what? Simply what? Small letter b. That means this small area, the A, therefore area, the A is simply equal to what? The width, which is simply B, times the thickness, which is the Y. This gives us the area, B times the Y. Okay, so we simply substitute this area into this equation. That simply gives us that the small intensity of moment, the M, is now equal to, this is Y times Young's modulus all over R, okay, multiplied by, in place of the A, we simply put in B times the Y, okay, multiplied by simply what? Y. All right. So from here now, I can have that the M is equal to, recall, I have y here, I have y here, and they are multiplying. So let's bring them together. I can rearrange this equation to simply be E all over R times y, that's putting this y in front, bringing this other y here, multiplied by y again, times b dy, okay? Of course, b times dy, same thing as b dy, okay? So this means that the m is now equal to E all over R. Y times Y simply gives us Y squared B dy. So let's call this equation 6. Okay, so at this point now, we've obtained the equation for the moment due to what? This smaller intensity of forces that emanates from the neutral axis to oppose the load that is being applied. Okay, that causes moment of resistance. Now, this is the moment of resistance, but we need to obtain the total moment. Of course, from what we are seeing there, it is actually what? A differential moment, a small intensity of moment. So we need to obtain the total moment. To do that, we simply what? Integrate. We have to integrate both sides of that equation to obtain the total moment of resistance. Okay. All right. So integrating, we have, okay, integrating, we have, all right. So we simply integrate the M to obtain total moment, and that's now equal to, but on this side, I'm seeing y squared dy, y squared dy. So which means I'm going to integrate the right hand side with respect to y, and therefore I will have a limit, and that limit is simply what? Integral from minus y all over 2 to plus y all over 2 of the what? The function given by the right hand side, which is simply E all over R times B times y squared dy. So I simply have this. So the limit of integration for the right hand side is simply from minus y over 2 to positive y all over 2. All right. So of course, if I integrate the m, I will simply have total moment, because integration is opposite of what? Differentiation. So once I integrate a derivative, it gives me back the total value. So if I integrate moment, the m, I will simply have total moment m, and this is now equal to, of course, Young's modulus here is a constant, so it will definitely has a value. Radius here is also a constant, it will definitely have a value. B here is also what? A constant, that's the width. So let's send this 3 out of the integral sign. We are simply going to have E B all over R integral from minus y over 2 to y all over 2. We are now left is simply y squared dy. Okay, sorry, it's a little bit jumped. Y squared dy. So we have this. So this is now equal to, okay, so I have E B all over R. Okay, so if I integrate y squared, I will simply have y cubed all over 3. Okay, so I have this. The limit remains y all over 2 minus y all over 2. That remains the limit. Okay, so moment is now equal to, let's now send this 3 out of this sign so that I will be left with y alone. So if I pull out 1 over 3 here, I will simply have E B all over, this becomes 3R. So simply what? Pulling out 3 over here, it becomes 3 times R, that's 3R. So I'm now left with my y cube left alone. Okay, limit remains y all over 2 minus y all over 2. This is now equal to, so we can now put in the limit of integration. We have the upper limit, which is y over 2. We have the lower limit, which is minus y all over 2. Now, this is now equal to, we have EB all over 3r. Okay, so we'll put in our limit. Upper limit comes first. That's simply y over 2 all to the power of what? 3, because we have y cube here. Okay, remember the lower limit is simply minus y over 2. So we'll simply put there minus y all over 2 all to the power of 3. So we have this. Okay. All right. So moment m is now equal to, so we'll put down EB over 3r. That is simply EB all over 3r now into, okay, of course, if you cube all this, it simply means y cube all over 2 cube. So y to the power of 3 gives us y cube all over 2 to the power of 3 gives us simply what? 8 all over 8 minus, let's open a bracket here, y to the power of 3. Please take note, minus y to the power of 3 still remains minus y cube. Okay, all over still remains minus y cube all over 2 to the power of 3 still remains 8. All right, so we have this. Let's send this man up a bit. Okay. All right, so you see how this. All right, so we obtain this equation. Let's continue from here. Moment is simply equal to EB, okay, all over 3r into, so we simply have y cube all over 8 minus y cube all over 8. All right, so we have this. So moment is equal to EB all over 3r into, this is now y cube over 8. Now minus times minus becomes plus, so I simply have plus y cube all over 8. So I have this. Okay. All right, so moment is now equal to, this is simply EB all over 3r, all right, into, so let's take LCM between these two. LCM here is 8, so I simply have 8. 8 divided by 8 is 1. 1 times y cube simply gives us y cube plus 8 divided by 8 here also is 1. 1 times y cube simply gives us y cube. Okay, so I'll simply have this. Okay. All right, so moment is now equal to, this is EB all over 3r into y cube plus y cube simply gives us 2y cube all over 8. And this is equal to EB all over 3r into, of course, 2 goes here is 1, 2 goes into 8 is 4. So I'm simply left is what? Y cube all over 4. So I have this. Okay, so I can simply write this to be moment is equal to, now let's segregate this. Now let 3 multiply 4, and of course we are simply going to have okay, let's just write the equation. We'll have E all over r, open a bracket, you see the same thing. We have here B y cube all over 3 multiplies by 4. Okay, simply 3 multiplied by 4, by cube is still the same thing, just put them in a bracket. So therefore moment is now equal to, so from here we have E over r, okay, into, here we have by cube. 3 by 4 here is simply 12, so that simply gives us by cube all over 12. Okay, so at this point, this function or this relationship by cube over 12, that gives us what is called the moment of inertia for a rectangular section. The moment of inertia for a rectangular section is simply bd cubed over 12, where d there is the depth, still the same thing that is presented here as y, by cubed all over 12. So this is actually what? Moment of inertia for a rectangular section. So that simply implies what? So we are simply going to say where I is equal to by cubed over 12. This is the moment of inertia for a rectangular section. Okay, that's the moment of inertia for a rectangular section. So in place of by cubed over 12, I'll simply replace the equation as what? Y. Therefore, the moment, this implies now that moment itself is now equal to E all over R times simply what? I. So I will have this. E over R times I. Okay, so if we have this, let's now divide both sides by what? I. Divide both sides by I. Okay, all right. So if I do that, I'll simply have m, which is the moment all over I, is now equal to what? E all over R. Okay, so I'll have m over I. Of course, if I divide both sides by I is off here, so it becomes m over I equals E over R. Call this equation okay, so I might not remember the last equation. I think it was 5 we stopped, so call this equation 6. Okay, call this equation 6. I think we stopped at 5. Now, at this point, notice this equation. This was equation 2 from the beginning that will obtain this relationship for stress. Notice now that this equation and this equation are sharing something in common. We have there that stress over y is equal to E over R. So conversely, we can say E over R is equal to what? Stress over y. Same thing happens here. We have m over I equals E over R. So conversely, we can say E over R equals m over I. So if E over R equals m over I, and E over R is also equal to stress over y, it means that we can now rewrite this equation as simply m over I is equal to E, Young's modulus all over R, radius of curvature, and Young's modulus over radius of curvature itself is equal to what? Stress all over y. So I simply have stress all over y. This equation is what we call the bending equation. Okay, this equation is simply called the bending equation. That's the bending equation. Okay, so that is how you derive the bending equation from first principle. All right, guys, I hope you find this video very helpful and educative. Please, if you do, I would like to get your thoughts in the comment section. And if you're new to the channel, please don't forget to hit the subscribe button to get updates on content like this. In the next video, we'll start applying this equation to solve numerous of problems in engineering. All right, guys, thanks and cheers.